Navigation is one of the oldest challenges faced by living things. To interact with our environment, we want to be equipped with navigational tools. Human exploration and trade were guided by the advent of more sophisticated navigational tools. Navigation has always had an element of estimation tied to it, requiring rigorous mathematics and coordinated communication. For early exploration, traveling by the sea opened multiple opportunities of access to new landmass, resources, and trade. The sextant allowed to measure angle between the star and horizon. Compass provided direction of Earth's magnetic north. Telescopes, spyglass, and binocular help navigate among different ships by extending human vision. Navigation was becoming science, but the instrument alone weren't enough. A navigator also needed knowledge of their environment and required maps. Coastlines were measured, hazards were recorded. The uncertainty in the ocean could only be cornered and not eliminated. Methods like dead reckoning would face problems with drift, tidal set, and wind direction. Navigators would face problems with imprecise sensors and unpredictable sea conditions. These errors would accumulate over days at the sea and compound into hazards. Convoys used to crash or be set adrift in the wrong direction. Traveling safely by the sea became a probabilistic nightmare, and solution to this problem was highly sought after. At one point, British Parliament announced a reward of £20,000 to help measure longitude of the ship at the ocean. The explorer could easily measure their latitude by measuring their angle with the North Star. The sextant informed the explorer of their latitude at the sea. Estimating longitude, however, required measuring local time at two places at the same time. Clocks were imprecise. John Harrison was the carpenter who invented the first chronometer. Using gems as low friction bearing and steel springs. This invention would revolutionize sea exploration and shift the probability of finding favorable sea to whoever owned the chronometer. On the foundation of the precise navigational tool, multiple trade routes and trade empires emerged. Modern trade with even denser sea traffic is possible with ever-precise navigational methods. They share the sea space with underwater vehicles and submarines. Controlling all this traffic requires precise communication and coordination.
MTS Agrippa, this is Bremen VTS. Alter heading to 00. Cruise rotation, proceed to channel.
Modern radar technology, ground station assistance to remote satellites, star tracker and sonar all exist to provide human assistance for navigation. While the question still remains for any modern navigating vehicle, where am I going, and how do I get there? At the answering end, we may not have humans anymore, for the question may need to be answered with such frequency not humanly possible. A ship crossing an ocean could eventually reach land and correct its mistake. A spacecraft traveling millions of kilometers through space does not have that luxury. A spacecraft must maintain its own orientation, estimate its movement, and execute correction with extreme precision. A spacecraft may carry multiple satellites into space, and the satellites require precise navigation not only to avoid collision but also for docking maneuvers. Modern navigation can be seen as a problem of measurement, computation, and autonomy. A MEMS acceleratometer contains tiny moving masses suspended by microscopic springs. When vehicle accelerates, these masses shift. The magnetometer measures Earth's magnetic field and provides directional awareness. A MEMS gyroscope uses the Coriolis effect. A tiny vibrating structure experiences a force when it rotates. This is the measure of angular velocity. Each measurement from the sensor can be distorted by the environment or inherent sensor defect. Gyroscopic drift and acceleratometer accumulating error are known problems, but together with inertial measurement unit, their defects can compensate for one another, and miniaturization into electronic component make them quite portable for small satellites. But we arrive at the same problem of drifting clock from the shipyard with the IMU. We need a stable clock in the role of the chronometer. With GPS lock of 4 satellites, one is able to determine the exact three-dimensional position. The accuracy and the reliability of the GPS network have made our life safer in land and in space. By measuring the travel time of the GPS radio signal, we are able to pinpoint 3D location. The satellites of GPS network are distributed in 6 orbital planes with line of sight coverage of multiple satellites at all times. However, the directionality prevents satellites at higher altitude from taking benefit of this network. These satellites must rely on guidance from ground station networks spread across the Earth. Or they may take advantage of rapidly rotating neutron star or X-ray emitted from it for guidance and navigation. NASA's Sextant mission used millisecond pulsars as celestial beacons to perform autonomous GPS-like spacecraft navigation in deep space. A different arena for navigation in space is planetary body exploration. Landing on a celestial body introduces another navigational challenge. The lunar surface is full of craters and unknown environment. Modern landers use camera, radar, and LiDAR system to map their surroundings. The OSIRIS-REx mission mapped the surface of the asteroid Bennu, selected sample and sent it back to Earth. The asteroid Bennu was mapped down to 5 cm pixel resolution. Another unprecedented challenge in the asteroid exploration is the ejected particles and rock fragments flying into the orbit of the lander. Autonomous navigation enables exploration where humans cannot easily operate. Robotic systems can enter lunar caves and go on asteroid missions and map their terrain. They are designed for making independent decisions. Space systems may encounter debris unexpectedly. Making autonomous decision for orientation correction requires autonomous navigation. Autonomously landing on unknown terrains require dependence on sensors they simply do not warrant. They are periodically offline, carry sensor bias, and accumulate error over time. By combining and weighting measurements among different sensors, we can get higher degree of accuracy. In an idealized environment, each maneuver of space vehicles create predictable results. However, much like at the sea, traveling at a longer distance means longer margin for accumulating drift. Truly interplanetary navigation may require far many corrections for unprecedented variables. The CW equations provide an elegant description of relative satellite motion, but much like at the sea, the assumptions and expectations are challenged by irregularities of radiation pressure, non-linearity of gravitational pull, and atmospheric drag. The predictive power of CW equation loses its edge in real scenario where disturbances are not constant, where not warranted linear dynamics or gravitational effects. Circular orbit is almost never the reference case. Modern navigation must therefore continuously estimate and correct these errors using onboard sensors and advanced estimation algorithms. Planning a trajectory and maintaining a trajectory are two different things. Vehicles like OSIRIS-REx compensate with robust and fast guidance system and hundreds of real-time decisions. Decision autonomy and trajectory optimization become even of greater value in interplanetary travel. The Hubble Space Telescope uses star tracker, reaction wheel, and fine guidance system for micro-adjustment of its orientation. The most commonly used tool in navigation for accessing multiple sensor sources of measurements and predicting current state is Kalman filter. The research into the field of Kalman filter has been so prolific that there are numerous new types of it. At the core of the sensor fusion is a weighing mechanism that provides a metric for level of trust it has over a particular sensor. That metric of trust is reiterated at each step and readjusted based on measurements. The Kalman filter predicts where the spacecraft should be based on the previous state and laws of motion model into its core. When the measurement is available, it corrects the prediction. The research into sensor fusion is also quite prolific. Some fusion implementation use human expertise in fuzzy logic implementation, while some rely on the training data. With increasing number of space participants and increasing number of satellite services, we can come to expect that the next navigation challenge is intelligent and autonomous navigation in space. Simultaneously, the problem of space debris is another major threat. With cooperative navigation, spacecraft gain awareness of their neighboring satellite and environment and make coordinated flight in space.
Insertion successful.
It will not be too far-fetched to say that the future space navigation tech will enable us to colonize other planets. and the cooperative robots will be the first one to do it.